Okay, so here we are again, continuing to read and try to understand the Transformers paper. Let me just make sure that this works. Okay. Yeah. Okay, that seems to be working. Great. I do have a meeting later on, so I can probably do just like 45 minutes this time, but let's see how far we get. Before we go back into this bit here on attention, which is where we stopped yesterday, I thought it might make sense to take a quick look at Andrej Karpathy's NanoGPT code and just quickly see if it's easy to kind of match what we have here in this notebook with what he's writing. If you haven't seen his video where he writes this NanoGPT code, I highly recommend it. It's highly educational and very entertaining as well. So I'd highly recommend it if you want to understand this. And he does write, basically, I think I mentioned this yesterday, he does write one half of this diagram basically from scratch using the PyTorch framework. And then just kind of, so this is the model file. I think maybe just kind of starting to look at this layer norm. It's probably a pretty similar code. Functional, what's this? Well, I guess he doesn't implement, for example, the layer norm calculation himself, like we did here, or like this article did. He uses predefined functions from the PyTorch library. Yeah, and then this will be exactly this. This is also what we saw yesterday. Yeah, I mean, I guess if you're writing this in PyTorch, it makes a lot of sense to do this. Self-attention, we're not there yet, so we'll skip that bit. But I think maybe comparing the code that we see in a few minutes with his code, I think might be quite instructional. And if I remember correctly, there was one bit here where he also made it easy to basically implement not just one half of the diagram, but the whole transformer architecture with the decoder and encoder bits. Okay, this is just multi-layer perceptron. Linear. And then he uses, maybe we'll see this also in the code that we're looking at now, I'm not sure, but oops. Yeah, Gaussian error linear unit, he uses this activation function rather than just a regular ReLU, which is this hard angled orange line here, he uses this slightly bendy line, and I think in the video he explains that this works better, or maybe this is also what he used in the original Transformers paper, I'm not sure, but something like this we haven't defined yet in our code, I think, but maybe I think they'll just use something from I mean, we just have the linear layer, I guess, with dropout. I don't know if our code uses this Gaussian error linear unit activation function. I don't think so. Yeah, I mean, this bit is basically, I think, what will correspond to what we're doing now. So token embeddings for the encoder, adding positional embeddings, and then going through the transformer blocks, which are just part of the diagram. And then linear activation, I think, at the end. Yeah, so maybe he just does the encoder bit and not the decoder. I think I may have gotten that wrong yesterday. And there's some code here to load parameters, etc. So I guess maybe this isn't as straightforward as I thought. So you know, looking at this while watching the video, I think will be much easier to understand. There's lots of sort of scaffolding here around this as well that helps load and train the data. But I think that the bit that we just pointed out, yeah, here, this in the forward function in the transformer class, probably in the GPT class, that will correspond to some of the logic that we're writing now, I think. I thought this would be more similar, but let's see. Train. This will probably just, yeah, this is just settings, I think. Yeah, this doesn't have any of the model logic or the model architecture. It's just preparing data, loading data, and then training the model using the PyTorch framework. I think this just has the image, yeah. Yeah, I think so. So all of the relevant code, except maybe parameters, etc., is here. And so this is basically just layer norm, the attention bit, self attention. So that should just be self attention. So I think that should just be this bit. Yeah. is just this bit, and then we have just the feed forward again with the layer norm. This is the attention bit that we're going to look at now, and then yeah, this multi-layer perceptron, I think, is just the linear. It's just the feed forward bit here. And then he also writes this position encoding bit and the input embedding bit, which I think we'll also get to later in this annotated transform article that we're looking at now. Okay, sorry. I thought the parallels would be more apparent, but it is the same structure, but just implemented slightly differently, or with slightly different code, but I think ultimately the effect is the same. Maybe we can get back to this later to also get a better understanding of how everything works. Okay, so back to this implementation here. Re-execute all of the code from yesterday. Okay, so let's jump into this again. Attention. An attention function can be described as mapping a query and a set of key value pairs to an output where the query keys, values, and outputs are all vectors. The output is combined with a weighted sum of the values, where the weight assigned to each value is computed by a computability function of the query with the corresponding key. We call our particular attention scaled dot product attention. The input consists of queries and keys of dimension dk, d sub k, I guess, and the values of dimension d sub v. We compute the dot product of the query with all keys, divide each by square root of d sub k, and apply a softmax function to obtain the weights on the values. Okay, again, this is pretty straightforward. Just takes q, k, v, these vectors or matrices, dot product, scales it. Okay, this I think is just for efficiency, or because the computational efficiency, so this doesn't really change anything in the logic. Softmax, and then again dot product with the values to get a selection of values or some sort of weighted average over the values, and the weights are computed by this vector product of q and k. This is, I think, what we've already looked at yesterday, and then in practice, rather than doing this sort of on one vector, here it says, in practice we compute the attention function on a set of queries simultaneously, packed together into a matrix Q. So we have a number of vectors, and rather than doing one by one, we just put this in a big matrix and do this big matrix multiplication, rather than doing sort of, so it's just doing this in parallel, so to speak. This makes it easy to parallelize if everything is packed into a tensor rather than just individual vectors. The keys and values are also packed together into matrices K and V. We compute the matrix of outputs as, so softmax of Q matrix multiplication with K transposed. This is basically just the dot product between the vectors in Q and in K. Then scale by this factor 1 over square root of d sub k, that's the yellow bit here. The first, what's this color called? Anyway, this color, this bit is the multiplication up here. The masking isn't done in this bit here, so we'll skip that. Then softmax, and then we do another matrix multiplication with v. That's the last bit. Sorry, what's this color called? Lilac? No. Purple? No. Maybe? Sorry, this isn't showing up, so let's maybe we can use this. Purple, yeah, exactly. Okay, so we understand this. Okay, yeah. This needs to match the query dimension. Okay, yeah, this is this. Then we do the softmax dropout. Doesn't say that in this, neither in this equation or in the diagram, but sure. And then this, yeah, this is just an implementation of this equation. The two most commonly used attention functions are additive attention and dot product attention. Dot product attention is identical to our algorithm except for the scaling factor. Okay. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer. Okay, so you can also do this slightly differently, I guess, but it's not what they're doing. While the two are similar in theoretical complexity, dot product attention is much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. Okay, otherwise you would need another. Yeah, I don't know. I mean, I don't know. I guess maybe I don't understand this, but isn't that? I mean, maybe this involves another activation function in between rather than just matrix multiplication. Maybe that's the difference. Because if it's just like a feed-forward neural network, then with a single hidden layer would go in hidden layer output. Well, so I guess you have sort of two matrix multiplications and yeah, I guess you have to compute the activation functions in between, rather than just doing one dot product. Sure. Okay. I mean, I don't know what the difference would be in complexity or sort of compute time, but let's just take it like they say here. Okay. While for small values of d sub k, the two mechanisms perform. This is, I guess, why they're doing this. The two mechanisms perform similarly. Additive attention outperforms dot product attention without scaling for larger values of d sub k. We suspect that for large values of d sub k, the dot product grows large in magnitude, pushing the softmax function into regions where it has extremely small gradients. Yeah, I mean, this makes sense, right? If you have large dimensions, even if the values are small in the vectors, essentially the dot product becomes like a really long sum, and you'll move out of the region where the softmax function has any significant gradient. And if the values are of similar size in each of the entries, like if they have like a similar scale, then the result of the dot product is roughly probably of order d sub k squared, right? It's just you multiply each of the entries and you get one entry times another entry of a similar scale, so that scale squared, and then that the number of times your dimension, the dimension, so d sub k basically times this scale squared. So if you divide by something of the order of this dimension, then you can scale the result back down to some rough value between 0 and 1 probably. Oh, I guess, yeah, this is basically what I just said, right? So to illustrate why the dot products get large, assume the components of Q and K are independent random variables with mean 0 and variance 1, then the dot product is Q times K, sum of these components, has mean 0, variance dk. So yeah, the variance will just be, the variance of this result is just the dimension d sub k, and so you can scale this back down. To counteract this effect, we scale the dot product by 1 over square root of d sub k, and then you get back to a regime between 0 and 1, maybe minus 1 to 1. And that is basically the regime where the softmax function has useful change, has useful gradient. Multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. With a single attention head, averaging inhibits this. Okay, so they use multiple, what they call heads. So basically they have multiple of these attention mechanisms. And then I think probably we'll see, well, so the one attention head is is an sort of an average over the values weighted by query and keys, and so you get an average of whatever this is. And so they're saying single head, you can only look at sort of a fixed subspace of the tokens, but if you allow for multiple heads, copies of this mechanism, then you can look at different pieces of the token stream simultaneously and use that as input to predicting the next token. And so multi-head attention is you just concatenate the output of several of these attention heads. H, I guess, yeah. H is the number of these heads. And then W0 where the projections are parameter matrices WIQ. Okay. So you give like different weights, I guess, to these outputs. Why would you add like another set of weights here? That I'm not really sure. Well, I guess the query keys and values are the same for all of the heads. So they use the same parameters in each copy of the head. So if you didn't have this, they would all do the same thing. This wouldn't really make any sense. And so you give each attention head a set of parameters, like weights, where they can tweak. Okay, yeah, so yeah, okay, now we'll get to, I think, the bit that I had a question about yesterday. How do we compute Q, K, and V from the input X? How does that connect to the input data? And then I guess what this is now doing is, I think, didn't we see that in the code already? This makes no sense. Like here, it does self-attention, giving it a copy of the input for each of these, right? So even though we kind of think of this as, okay, here are the values, keys, and query, so the values are kind of like, okay, here are the inputs. What would you like to know about them? I think this is how important each bit is. You know, at this stage, these are all just X, X, X. It's just the input copied 3 times, right? And then finally here, I don't really understand why it doesn't have any sort of parameters. You know, there should be like something similar here, right? Like if one head of attention doesn't have any parameters, then this is just, okay, takes the input, does something with just input value, scales it, softmax, okay, you're done. This doesn't really make, you know, there aren't any parameters here that you can sort of tweak. But I guess once you're here, if you use something like this, Now you have each, so for query keys values, you have weight matrices, and then you have a weight rate matrix at the end for each of these individual heads, where you can now tweak, okay, how much do I want to look at the values? How much do I want to look at the query? How much do I want to look at, query and the keys? And then you can now tweak these parameters. So each head of attention can weigh different things here. And then, you can weigh again. How much do you want to weigh each attention head? So in this work, we employ h equals to 8 parallel attention layers or heads. For these, we use d sub k equals d sub v equals d model over h 64. Okay, I guess this is just another choice that works. I mean, you have to, I haven't kind of thought this through, you have to, like, these different dimensions need to correspond to each other so you can do matrix multiplication, but then apart from that, you can probably, scale these up or down a little bit to improve performance or improve accuracy. Due to the reduced dimension of each head, the total computational cost is similar to that of a single head attention with full dimensionality. Yeah, so I guess, yeah, that's what I thought, right? You could, the maximum dimension you can do here is the dimension of the input, I think. And you could do one head of attention that's the full model dimension, so the full input dimension, but instead they divide this up into 8 different heads. So, and then instead of, doing sort of 8 parallel full dimensional heads, they give each head an equal subspace, basically, of the input dimension. Okay. We will add this here. Let's take a look at this code real quick. This is okay, it just extends and end module, so nothing fancy there. Make sure that you can, not sure if this is required. Like, you could probably have attention heads with an unequal, they don't need to be the same size, I guess. But anyway, in this case, they want to be able to equally distribute the dimension among the different heads. Okay, this is, I think, does not need to be the case, but makes it a lot easier to build this architecture. Implements figure 2. Okay, what's figure 2? I'm assuming it's just this. Mask, okay, we skip that. Do all of the linear in projections in batch from D model. Okay, why do you have this linear layer here? Maybe this is just this bit, I guess. Query key value lin dot view and batches. What's this lin? is this? This must be... Oh, okay, so, sorry, this is this one. So, okay, so they have like linear layers here. Do a linear layer on input. Okay, and then just quickly, let's take a look at torch view. What's it, view? Returns a new tensor with the same data as a self tensor, but of a different shape. Shares the same data and must have the same number of elements, but may have a different size. Okay, oh, that's nice. Okay, it's very nice. I think that's why everybody's using Torch, right? It's quite straightforward, right? It's really, sorry, this is a bit of a tangent, but I think the idea behind the framework is really nice, right? So you basically all you do is for each layer or each sort of component that you have in these networks, you just create a class that extends this nn.module neural network module class, and you give it a forward function where you define what it does, and then you can just sort of maybe this is easier to do in to see now in properties code. Basically, you just do. Oh, he's also using this. Interesting. Okay, but basically you do. Where is like a good example? Yeah, right. You just do okay. Compute the next bit, and it automatically understands that, you know, by executing it in this order, it automatically understands that this is the network structure, and then you can just give it, okay, here's how I want to compute it in this order. You give Torch this code, and then it understands that, okay, this is the model. And then it knows how to train it, right? It's really nice. And then also it has all of these quality of life functions, right? Like this view here where you can look at a matrix. What's that called in pandas? You know, you can look at it in a transformed. You know, you can shift the dimensions around and transform the matrix into a different structure, but still the same values, and that makes it super easy to apply functions that maybe expect the data in a slightly different dimensionality, right? It's really nice. This is interesting. Okay, so it does these linear transformations, which is essentially just you know, giving it parameters to do these weight matrices here. Do this for all of them. And then do the attention with query key value. That's this. Basically, okay, for each head, you just do scale dot product attention. Bring this back together. Free up memory. Okay, sure. And then in the end, do another linear layer on top. Okay. So basically this orange box here is what we just saw, right? So we do one linear layer, so one set of parameters to tweak query key value, right? We do the self-attention, which is just, okay, do dot product key of query and key, scale it, do a dot product with the value, and then we do another layer, which is, we do another linear layer, which is just essentially, okay, where is it? Okay, here's another weight matrix, W0, or maybe this is WO, I'm not sure. Maybe WO for output. do another weight matrix so you can weigh these different heads. This is quite straightforward, right? I thought this would be much more. I don't know. I thought there would be something more, but it's just okay. Here's the input tensor. Here's a linear layer to give you some parameters to kind of weigh it, and then you take 3 copies of that. Do some dot product between them, and then there's another. Okay, here's another set of parameters to tweak the weights. Then you do the layer norm. Here's another linear layer, and you're kind of done, right? Yeah, I think it would be really interesting for different models to kind of understand, okay, so once you train this network, what are these weights that you get here, right? Like what are the values, what are the keys, what are the queries, where does the network think that you need to look? And I think in the original paper, which I looked at some time ago, they have some illustrations in the back that shows you this. I wonder if people actually look at this, like at OpenAI or something, if they... Yeah, this is figure 2, right? I think in the appendix they have that. Yeah, so they have like some attention visualization diagrams, right? So where here's a sequence, this is the self-attention, right? So it is in this spirit that the majority of American governments have passed new laws since 2009, making the registration of voting process more difficult. End of sentence, pad token. And so the attention connects this token to itself, to this bit in the sentence, so making more difficult is like a strong connection. So that it like somehow it understands this grammatical structure, making more difficult. Or here, the law will never be perfect, but its application should be just. And so it connects its to law and application. So because you know the law will never be perfect, but the application of the law is what this should say, or what this means, right? And so somehow through training, it can generate these connections within the stream of tokens that roughly correspond to some sort of grammatical connection or meaning, and that's why it's why it's so powerful, right? But just looking at the code here, like it's not clear at all that this would come out. It's not clear at all that it could actually do that, right? Basically, you're just giving it parameters, right, to say, okay, you can look at other pieces in the sentence, and you're free to create these weights as you wish. But like the fact that these grammatical structures emerge just from showing it tons and tons and tons and tons of token streams, right? It's totally not clear to me from just looking at this. I mean, I guess it'll be optimized, or it'll be there'll be some gradient descent that basically optimizes for that. Well, I guess you could say, assuming that in this huge data set that presumably you have when you train these sorts of models, if in the token stream examples if there is a correlation between, okay, this token here and this token, this token here and here and here, there is a correlation that then determines what the next token is. Well, I guess if grammar, determines how sentences can be formed, then maybe the model might be able to catch that, right? And the fact that it does, I guess, is yeah, it's not surprising. I guess this is how it has to be, but it's kind of surprising that it works just from this simple structure, right? The network structure is really simple. Okay, so I need to get going. So we'll end the stream here. But I think we've created a basic understanding of how this attention works. And then I think in the next stream we'll take a quick look at the Nano GPT code again, just to kind of see if there's anything we can learn from that, because it should basically be the same structure. And then continuing to read through this, and then we will see also the embeddings for the input, positional encoding, and then yeah, I mean that will be all of the components basically, and then we can train it, which I'm assuming they will do through the Torch framework. Yeah, they'll just, I think, I guess the training and optimizing these bits are sort of technical details that make this possible in the first place, right? So there's a lot of, I mean, the model is quite simple, but you know, making this actually work on existing hardware and making it efficient, making it not overfit, making it have, you know, a nice model that involves a lot more tricks that we'll get to later. But like the theoretical bit, I guess, is surprisingly straightforward. All right. Thanks so much. This was fun. See you in the next stream.